Hi there, this is our second video lecture on coastal processes, and this one covers continental margins, depositional and erosional features. When we learned about topographic maps earlier in the semester, we learned that the word topography refers to differences in elevation on the Earth's surface. Similar to the word topography is bathymetry. Bathymetry just refers to the variation in depth of the sea floor. So topography is on land, bathymetry is how we describe the depth of the ocean. And part of what determines what the bathymetry of an area looks like is related to whether the margin of the continent is either a passive or an active one. Continental margins can be either passive or active depending on the plate tectonics that are going on. So this is somewhat of a review from the fall. So down below here on the left, we have an example of what is a passive continental margin. A few things to point out. Here on the right side, this little piece of crust here, this is the oceanic crust. And oceanic crust ranges between, on average, 5 to 10 kilometers in thickness. Over on the right side of the picture where it's marked at 40 kilometers thick, again, this is an average, this is continental crust. So continental crust tends to be thicker. It is more buoyant. It is less dense than oceanic crust. It is made out of crystalline rocks like granite and some metamorphic rocks. Whereas oceanic crust is thinner, it is denser. It is made out of rocks like basalt and gabbro, which are very mafic and have a lot of dark iron and magnesium rich minerals that compose it. Also remember that the lithosphere is composed of the crust and the uppermost part of the mantle. So we've got the continental lithosphere on the left and the oceanic lithosphere on the right. If what you are looking at is a passive continental margin, what that means is that some area to the right is where the new oceanic crust is being made. And as that original continental crust was pulled in this direction and it started to break, new oceanic crust came up from below. And so you've got oceanic crust being formed here because the continental crust has been stretched. Maybe there's faults in here making all these cracks where it's gotten thinner. And so you have this kind of continuous piece, which is one big tectonic plate. So it started off all as continental and it got pulled apart and stretched so thin that eventually you had new oceanic crust come up and form. And you can see what these look like on the planet even just by looking at Google Earth, because you'll have this kind of gradual transition from continental to oceanic crust. In fact, my dissertation was on the Gulf of California, which is a section of the Earth where these stretched pieces of continental crust have pulled apart so thin that you have new oceanic being formed in the middle. And so what you can see here is there are these features where things have been stretched and fault blocks have slid down. And then on top of it, sediments have piled on to this thinned crust, making what's called the continental shelf. So this flat piece coming out here is what we call the continental shelf. It's composed of sediments that have eroded off the continental crust. This is the continental slope. The rise is just kind of the transition between the slope coming all the way out here onto the flat oceanic abyssal plain. So this is a diagram showing a passive continental margin. In contrast, an active continental margin is what you have when you've got more tectonic activity going on. So over on this side, we've got the lithosphere subducting underneath in this location, underneath the continental lithosphere above, and that kind of dewatering of the subducting plate is causing flux melting, which is making like all the little volatiles come up in here and lower the melting point, which means that this base of this crust is melting and it's coming up here and forming volcanoes right? So this is like the Cascade Range. We've got subduction zone off our coast in Oregon. We've got a big trench or wedge of sediments, and you've got volcanoes here on the right. So because these two types of margins are very different tectonically, the features that you're going to see at the edge of the continent here are going to look very different than the features that you're going to see at the continent on this side. So let's use South America as an example. If I were to draw a transect, just like this, right across South America, just by looking at this Google Earth image, I can figure out where the active and passive continental margins are. Remember that the color variations that you see in Google Earth are indicating whether or not the bathymetry is high or low. So take a minute to figure out which side do you think is the passive margin of South America. Remember that the big green space, right, this is all continental crust. So this is all continental crust. Okay, and then out here is your oceanic crust on either side. Okay, so if we're taking a transect across South America, the side on the left is going to be your active continental margin. You guys should know this because this is where you've got the Nazca Plate subducting underneath the South America plate. There is a big trench that is kind of darker colored, indicating a deep trench. Okay, and that trench is here. So you've got this trench, you've got a subducting plate going underneath. This is pretty active. You can tell this just from the Google Earth bathymetry that this looks very different than the other side. If you look at the other side, it looks more like our passive continental margin picture. So if you follow this transect to the east, and you'll see how as it crosses kind of the southern part of Brazil, it goes across this relatively shallow, flat section. This is underwater, but it's not very deep. And that is your continental slope. So it's your flat, shallow water, and then it starts to go off down here, off the continental shelf, down the continental slope. So what are some depositional features we see on both passive and active continental margins? Well, you guys are most familiar with beaches. Beaches are just deposits of sediment along any shoreline. Beaches are mainly composed of rounded quartz sand grains. There are some exceptions to this, but if you were to take a census of all the beaches around the world, the majority would be rounded quartz sand. So why are these grains rounded? You might remember from when we talked about sedimentary rocks that the farther distances that sediments travel, the more they hit together, they end up knocking the little angularities off of those clasts. So whether or not you've got a cobble or a piece of sand, they're going to get rounder the more they smash into other things. And at the beach, the sand is constantly being rubbed against each other as the waves go in and out and in and out. They end up rounding all those little tiny particles. So why then is beach sand mainly quartz? Remembering back to when we studied mineralogy in the fall, quartz is SiO2, and quartz is one of the harder natural minerals that forms. It also just doesn't wear down very easily. So whereas things like feldspars and micas will break down and turn into clay, quartz is really, really hard and hardy and can withstand a lot of physical and chemical weathering. So whereas other minerals might dissolve or break down or become ions in water that you can't see anymore, quartz is left behind. So the last piece is, why is most of the stuff at the beach sand? And when we talk about sand, we're talking about a very specific sized particle. Remember that it takes different amounts of energy to move different sizes of particles. So giant things like boulders need a whole lot of energy. Sometimes they chunks to make a conglomerate like fall off a literal cliff face. So gravity is pulling it down. Sand needs a little less energy to move. And then when you're talking about particle sizes like clay and silt, they don't need much energy at all. When material comes to the beach, if you are a tiny clay or silt sized particle, you're going to be easily washed away and out into the deeper ocean. Sand just happens to be the perfect size to kind of stay relatively put, but it's not going to get washed out quite away with rain or a wave. And in general, waves along the shoreline aren't going to be moving giant boulders either. That being said, there are always exceptions to these three things. So this is one example of a white sand beach in Florida. You'll notice that the color, that white color, is not actually quartz sand. This sand is from the erosion of limestone. So this is limestone sand and tiny, tiny shells. And this is because the bedrock in Florida is primarily composed of limestone. So the composition of your sand really depends on the rocks that you are eroding and the sediments that are ending up at your beach. This is another picture. This is a beach in Oregon. This is a beautiful area called the Yaquina Head Natural Area, and there's a lighthouse there. And what you'll see is that their beach is entirely composed of rounded basalt cobbles. Remember that Oregon has had lots of big basalt flows, and some of those have made it all the way out to the coast. So this kind of piece that's jutting out here is a large basalt flow, and the rocks that later turned into these cobbles have eroded off these cliffs and then just kind of rolled around in this bay. So the rocks haven't traveled very far from their source, but because they keep knocking together like giant marbles down there, they're super rounded. Hawaii is also known for some really cool black sand beaches. And again, this is the result of the sand being sourced from volcanic rock. So basically basalt that has been ground down more into a sand-like size. That's a little different from these cobbles, but it's the same general idea. In our last video, we talked about how underneath the wave base, which is a depth of half the wavelength, the sand down here in this region is not really activated at all by the waves above. And so the lower you get in the water, the lower the energy or the less motion that sand is experiencing. In this region, though, all of that sand is very active. You have breakers coming in as the bottom of those waves drag on the bottom of the seafloor, and that sand can move quite a bit. It also experiences interaction with the tides. The wind can also blow some of the sand on the beach to form sand dunes along the shore. And many of you have probably been to areas along the Oregon coast where there are sand dunes in between the ocean and kind of housing communities to the back. So you get these piles of sand. And then back here in this lagoonal area, the definition of a lagoon is just kind of a still water zone or wetlands, kind of a marshy area where there's really low energy. So you have some sand, but also a lot of muds and silts that can settle out of the water. There's sometimes lots of animals and organic material. But lagoons are in general really calm water areas, and they can be interconnected to the ocean. And I'll show you some pictures. So they can be tidally influenced, but they're not getting waves. In the previous video, I talked about how when waves come into a shore, they're usually hitting it at some sort of an angle. This is due to, wind doesn't always hit shore straight on. So as it's blowing these waves and they hit at an angle, particles and water, they swash onto the shore and then they backwash off, and then they swash on and they backwash off. And the backwash goes straight down perpendicular, but the swash can be kind of to the side. And that motion of swashing and backwashing can move sediment particles along the edge of the land. And this is what is the longshore current, and it creates this effect called longshore drift. So longshore drift can result in a couple different features. One is called a bay mouth spit. So a spit in general is just any sort of kind of piece of sand that's kind of sticking out somewhere. A bay mouth spit in particular is one that's like trying to cover the mouth of a bay. So it's moving across some spot where you've got river water coming down and meeting the ocean. And then you've got this spit of sand that's being created and kind of curled around the corner here. A bay mouth bar is essentially the same thing, but sometimes it can actually cut off the river that's draining down to the ocean. So it can make this kind of turn into a lagoonal area back here that fills up with water because it gets blocked off or maybe finds another path out to the ocean. And if you have one of these spits that gets isolated, it's just, we call it a barrier island, like this guy over on the right. Barrier islands can actually get really long. So as all the sand is moving along, they can make these long linear features, like over here in this image. So barrier islands also work as kind of this protective fence line. So when storms and big waves come in, they're kind of, they work as a protective shield so that the interior does not get quite so messed up. But because barrier islands are just made out of sand, they're not made out of any bedrock, they're super mobile. And when a storm does come through, it can actually cut right through them. So this image down below shows how during a storm that came through, it eroded right through this barrier island. As people, we have a hard time envisioning the land beneath us as being mobile because we have really short-term memories and we don't mesh well with the geologic timescale. So there's actually, in this photo, there's a road that comes along here that was just totally cut off. And if you were somebody who had a house, over in this section, you might now be completely isolated from the mainland, depending on what the geometry of this barrier island looks like. One place that's really well known for its barrier islands is Florida. So I'm going to zoom in on this section of the map that I've got the red square around. This is the Tampa, St. Petersburg area, and you can kind of see Tampa Bay there. So I zoom in here, there's Tampa Bay. And what you'll notice is, see all these tiny little pieces. These are all barrier islands of sand. So these things are moving along. If you look down below here, you can tell that the longshore current is going this way because you've got this kind of piece of sand that's jutting out in this direction. So in general, the wind must be blowing like from this direction to make the longshore current go along the coast of Florida. So we've got all these different barrier islands here. Here's a zoomed in portion of the one I was just showing you. This island is in particular called Anna Maria Island. Back in this region back here, this is more of a lagoonal area. So calm, low energy, probably more muds and silts filtering out and layering on the bottom. And up here is where Tampa Bay and all the rivers that drain into Tampa Bay are flowing out to the ocean. So I said before that barrier islands are constantly moving because they are just sand. Again, remember they're not bedrock. There's nothing hard underneath them. And this makes it kind of an interesting place if you're going to build a beach house. So here's an example of it's zoomed in on this barrier island, and you can see all these houses and hotels and restaurants built along this tiny, tiny, skinny spit of sand. And in fact, if you look over on this side, right, this is where they have built houses on piles of sand that they have made. So these linear things are not natural features. They are not houseboats. They are actual homes that Floridians have built on essentially land that they have made by dumping rock and piles of sand into the ocean. Another thing to remember is that these houses and everything are sitting basically a few feet above sea level. So you're on a skinny spit of sand a few feet above sea level. When they build new houses in these areas, they actually build them way up on stilts because flooding from hurricanes is so frequent that they want the water to go underneath your house. But if a hurricane actually comes through here, it can cut through this island pretty darn easily. So thinking about like another side of the United States where you might have cliffs, Florida isn't very cliffy, but if you think about somewhere like Oregon, we often have, steep layers of rock going right up to the ocean. And in areas like where we live, you can get these erosional features called wave-cut cliffs. So the zone between the low tide and the high tide can make this interval where you're going to have a lot of interaction with waves and they'll erode the base of a cliff, which will then kind of, crack off pieces along joints, which will then plunk into the water. If the erosion for that cliff happens over a long enough period of time, what you'll end up with is a long, wide platform where it's just cut back and back and back and back. And when the tide goes out, you can see this flat piece. So in this photo down in the lower left, this is a big flat section of rock that has been eroded by waves traveling across it between high and low tide over a long, long period of time. Along the Oregon coast, you guys have probably noticed that the coastline is not this perfectly straight thing. So the reason why you get variations in kind of the edge of a coastline, basically headlands and bays being formed, is because sometimes you've got sections of rock that are harder and more resistant, and then other times you've got types of rock that are more crumbly and easier to erode away. So when you have waves coming in, like in this phase 1 on the right, the harder rock is going to be more resistant and you're going to end up eroding out these little dips in bay areas. And when that happens, there's a variety of different features that can form. So maybe you start with some erosion of a wave-cut cliff down here, and then because the rock might be somewhat fractured, the material can drop into the water and form some sort of sea cave, and these are common on the Oregon coast. As that cave gets bigger and bigger, it might end up breaking all the way through and becoming a sea arch. So you can actually look through it at that point. If that sea arch then collapses or breaks down, you're often left with these features that we call sea stacks. So these are kind of like as erosion is progressing in this particular area, different, there's an evolution of features going on. We have a lot of sea stacks on the Oregon coast as well. This is a picture down from the southern Oregon coast, but you guys are most familiar with probably Haystack Rock, which is a giant sea stack. So the rock that Haystack Rock is composed of used to go all the way out to Haystack Rock. It used to be one big solid piece that looked something like this feature. And then as an arch formed and then that broke down, it just left the chunk of sea stack rock out there. Sorry, I meant haystack rock. Um, so the last piece on here is this kind of little stretch of sand that connects up kind of the main rock on the coast with those little sea stacks, and they refer to this as a tombolo. This picture and the examples with it are also in your book, and you're going to need that in order to do the lab assignment. All coastlines, whether on an active or passive margin, can be classified as either emergent or submergent coastlines. An emergent coastline means that the sea level is lowering or experiencing a regression, or the land is rising, or actually both could be going on. So what this will look like is maybe you're starting off here with sea level at a certain point. And you've got this wave cut bench being formed and it's eroding the cliff face right here that's breaking off and falling into the ocean. And if the land surface rises, then the new cliff will be forming down at this level. So you end up with this exposed wave cut bench that has been uplifted. So either the land could rise or sea level could actually just fall down. The effect is going to be the same. You can tell if a coastline is an emergent coastline by looking for evidence of tidal flats getting larger and larger, having, like I said, those wave cut benches exposed. Beaches tend to be wider and stable, and if you have a river coming into the ocean, it might show a delta building outward. Submergent coastlines are going to be the opposite. So in this case, sea level is rising, which is a transgression, or the land is subsiding, which means sinking, or both is happening. So here's an example of what a submergent coastline might look like. So we're starting with kind of regular or low sea level here on the left, and you've got these kind of V or U-shaped valleys with rivers coming down them. And then over time, as the sea level rises or the land sinks, either one, the ocean will end up flooding in these valleys. And we're going to talk about that more when we talk about glaciers, but often if you have a U-shaped valley there and it fills in with water, it forms what's called a fjord. So we can see this with flooded valleys, narrower beaches because that water has come up, leaving less of that beach exposed. Wetlands can get submerged, and maybe something that didn't used to be an island, maybe like a peninsula, becomes an island as it becomes a submerging coastline. So because coastlines are constantly changing and sand is shifting and moving, people get really annoyed about this. So it can be really inconvenient if you have built your nice beach house right on a coast and then you realize that the beach happens to be moving to the north, away from you. So as humans, we do all sorts of wonky things to try and force coastlines to stay the same, to stay static. So one of the things that we tend to do are we put in these things called groins. And a groin is a wall that's built perpendicular to the beach. And the whole idea with a groin is that it's trying to prevent the longshore drift or the longshore current from moving sand along the beach. So this is a picture of, I believe this might be South Carolina. And you see these features coming out. These are the groins. Sometimes they're made out of sand bags. Sometimes they're more permanent hard structures like concrete or maybe large rocks and boulders. But in any case, you can tell the direction of current flow in this particular situation. The longshore drift is headed this way. And the reason you can tell is that you can kind of see this sawtooth pattern with the sand. So it's building up in this area, and then the water comes around and it cuts out and erodes from this area. So deposits on one side and erodes on the other side. So probably this area that looks like it has a bunch of fancy, expensive homes has put this in so they can keep in their nice sandy beach to walk along. Another area where they've used this idea is the city of Chicago. So this is Lakeshore Drive along the city of Chicago, this road. And Chicago is built right on beautiful Lake Michigan. Lake Michigan is one of the Great Lakes, and the Great Lakes are so big that they kind of act like an ocean. So they get currents um, similar to the way an ocean current would occur. So you can even tell, looking at the spit down below, that the flow of the water here is moving this way. So they're experiencing that wash and backwash that's moving sand along, and they put in these groins to keep that sand from scouring away and moving too far. So this little hook here shows at the bottom, shows where all that sand is kind of being caught up, but they put in human-made structures to keep their beaches really nice right downtown in Chicago. Another type of structure that people put in to make life more convenient is a jetty. So a jetty is basically this linear structure. We've got a couple of them. There's one here, there's another one here, another long one at this point that's built to protect the entrance to a harbor. These are often put on at the mouths of river channels to help ships go in and out. These particular jetties were installed at the mouth of the Columbia River. So this is the Columbia dividing Washington from Oregon. And you can see the town of Astoria down below. So you've got these long jetties. They make it safer for big transport ships to come in and out of the river. So coming into the port in Astoria and then all the way up into Portland, essentially. These jetties also protect it from any sort of longshore drift. So the mouth of the Columbia isn't going to have like big sandbars necessarily out here. And I believe they do dredge those as well to keep it clear. So jetties in this case are primarily built from big rocks. So this picture is showing this southernmost jetty, some people working on it. And those boulders that they put in are really huge. So here is a picture for scale. Like there's a little guy down there and it's showing these are not small rocks. Does it mean that they're going to be there forever? Definitely not. They have to put these in place, kind of like lock them in. They don't just dump them in a giant pile. But they can erode and get damaged over time, just like anything. The last crazy thing, well, not the last, but the last crazy thing I'm going to talk about that humans do is called beach nourishment or beach renourishment in some cases. And what happens is when you might lose a bunch of sand on your beach from either a storm event or longshore drift that's just moved it along over time, you go to replace that beach sand by pumping in sand from either offshore or lugging it in on big trucks. So this is a photo of Hilton Head, South Carolina, which is a well-known place for vacationers. And you can see in the before picture, the beach was kind of getting kind of skinny out here. And, you know, they might be worried about it eroding back and taking out some houses. But in general, because these areas depend heavily on income from tourism, being a vacation destination, they want to make sure their beach looks as fantastic and as wide as they can possibly get it. So they spend a lot of money on transporting sand back up here and plopping it on to make this a thicker, wider beach. Here's another example of kind of what this looks like when it's in the process of doing beach nourishment. There's a big pipe that is pumping water from offshore that's like half water, half sand, and then they take these little bulldozers and they kind of build it up so they have a bigger beach platform. This is also South Carolina, but this is in, I think it's Myrtle Beach. But this sort of beach nourishment happens in lots of places. Down in Florida, it's really common. It costs tons and tons of money, which basically the taxpayers end up paying, whether you have a house on the ocean or not. But they think it's worth it because it continues their tourism. But there's lots of pros and cons from moving all of this giant quantities of sand. In the post for this week, I linked a video that has this clip in it from Myrtle Beach showing how they pump the sand out and rebuild these beach environments. So you should check that out.